How Neanderthals engineered the world's first industrial-strength superglue. Where do you find industrial-strength superglue when you are standing in a frozen prehistoric forest 200,000 years before the invention of written language, metal pots, or chemical labs? How did Neanderthals, long dismissed by modern pop culture as slow-witted, primitive cavemen, engineer the world's very first synthetic material? And how did their secret chemical recipe solve one of the greatest manufacturing challenges in human evolutionary history? To answer this incredible scientific mystery, we must first dismantle the modern misconception that natural glues are easy to find in the wilderness. You might imagine an early human walking up to a pine tree, scraping sticky tree sap off the bark with a stick and smearing it onto a spearhead. But crude pine resin or tree sap is a terrible adhesive for heavy hunting weapons. Raw tree SAP stays sticky and wet in warm weather, attracting dirt and slipping under pressure. When the temperature drops below freezing, raw tree sap turns extremely brittle, shattering like delicate glass the instant your spear strikes a heavy mammoth bone. Furthermore, the European forests occupied by Neanderthals were dominated not by pine trees, but by vast stands of white birch trees. If you walk up to a white birch tree and cut the bark, nothing leaks out. Birch trees possess zero liquid SAP, zero sticky resin, and zero natural gum dripping from their trunks. So how did Neanderthals transform the dry, papery outer bark of a birch tree into a pitch-black, rock-hard, industrial adhesive that lasted for tens of thousands of years? The breakthrough answer was uncovered by paleoanthropologists conducting excavations at the famous archaeological site of Campitello Quarry in central Italy. In a landmark study led by Dr. Paul Mazza from the University of Florence, scientists discovered two flint flakes deeply embedded in organic black residue, dated to over 200,000 years ago. Chemical analysis using gas chromatography and mass spectrometry revealed that the black residue was pure birch bark pitch. This single discovery shocked the scientific community. It proved that Neanderthals were manufacturing synthetic adhesives in Europe more than 100,000 years before modern Homo sapiens ever stepped foot on the continent. To understand why this discovery redefined human prehistory, we look to the groundbreaking experimental archaeology research of Dr. Patrick Schmidt from the University of Tübingen and the Friedrich Schiller University of Jena. Dr. Schmidt and his research team set out to recreate the exact physical conditions required to produce birch bark pitch using only Paleolithic technology. Their experimental findings revealed that birch bark tar cannot be created by simply burning bark over an open fire. If you burn birch bark in the open air, the bark quickly catches fire, turning into useless white ash and black smoke. To extract pitch from birch bark, you must perform a complex chemical process known as dry distillation, or pyrolysis. Pyrolysis occurs when an organic material is heated to extreme temperatures in a strictly oxygen-deprived, airtight environment. Under these precise anaerobic conditions, the complex organic molecules inside the birch bark, specifically betylene and lupil, break down and transform into a dense, volatile gas. As this gas cools, it condenses into a thick, sticky, pitch-black liquid tar. But here is the catch that makes Neanderthal intelligence so mind-blowing. The temperature window for successful birch pitch pyrolysis is extraordinarily narrow. The temperature inside the chamber must be maintained between 250 degrees and 400 degrees Celsius. If the temperature drops below 250 degrees, no pitch condenses. If the temperature spikes above 400 degrees, or if a single crack allows oxygen to leak inside the chamber, the pitch instantly ignites and burns into worthless soot. Think about what this precision temperature control required. Neanderthals did not have digital thermometers, steel pressure cookers, or airtight glass valves. They had to control chemical pyrolysis inside subterranean pits using dirt, wet clay, turf, and campfire embers. They had to monitor the heat using nothing but their senses, reading the color of the smoke, feeling the radiant heat of the soil, and listening to the soft sizzle of condensing tar beneath the earth. To see how this extraordinary chemical process worked on the ground, let us reconstruct a concrete scene from 120,000 years ago in a limestone rock shelter along the Rhine River in central Germany. Imagine you are a 30-year-old Neanderthal craftsman sitting near the edge of a cave shelter on a chilly autumn morning. The ground is damp, covered in yellow birch leaves, and a cold northern wind is sweeping through the valley. Beside you lies a pile of freshly harvested white birch bark peeled in long, flexible strips from nearby trees. You do not throw the bark into the central campfire. Instead, you use a sharp flint hand axe to dig a neat, cylindrical pit into the dense clay soil beneath your feet, roughly 8 inches deep. You take the thin strips of white birch bark, roll them tightly into compact cylinders, and stack them vertically inside a small hollowed-out stone container. You flip the stone container upside down into the clay pit, sealing the edges with thick, wet mud. You scrape damp dirt over the entire structure, packing it down firmly with your bare palms until not a single pocket of air remains. You have constructed a miniature, subterranean, oxygen-deprived distillation chamber. Now comes the master stroke of fire management. I'll build a bright, hot campfire directly over the buried chamber. You do not let the fire burn wildly. You carefully feed it specific hardwoods, building a dense bed of glowing orange coals that radiates steady, uniform heat downward into the clay soil. For 3 straight hours, you tend to the fire. You add damp moss whenever the embers burn too hot, keeping the temperature locked inside that narrow, invisible golden zone between 250 and 400 degrees Celsius. Deep beneath the fire, inside the pitch-black, airless clay chamber, the birch bark begins to sweat. The betulin molecules break apart, vaporizing into a thick chemical steam that trickles down the cool inner walls of the stone container, pooling at the bottom as a dark, viscous liquid. As the sun begins to set behind the western ridges, you let the campfire die down to gray ash. You allow the soil to cool completely so oxygen does not ignite the hot vapors. You carefully scrape away the dirt, lift the stone container, and look inside. Coating the bottom of the stone is a thick, glistening pool of pitch-black liquid tar. But your chemical work is only half finished. Raw birch tar is still too soft and malleable when warm. To transform this sticky liquid into an industrial-strength composite glue, you reach into the cold ash pit beside you and pull out a handful of pulverized wood ash and red ochre powder. You knead the fine mineral dust directly into the warm pitch using your thumbs. This mineral additive acts as a chemical filler and plasticizer. It alters the molecular structure of the tar, increasing its tensile strength, preventing shrinkage as it cools, and making the final product resistant to brittle fractures during high-impact strikes. You scrape the warm, pliable compound onto the end of a wooden stick, forming a thick ball of dark paste. As the glue cools to room temperature, it hardens into a tough, solid thermoplastic resin that can be stored indefinitely, carried in a pouch, and remelted over a warm flame whenever tools need repair. You take a newly flaked flint point, heat the ball of pitch over a small ember until it becomes pliable. Press the black adhesive into the notched end of your ashwood spear shaft, and set the stone blade deep into the socket. Within 2 minutes, the glue cools and hardens into a rock-solid bond. You lift the 6-foot weapon and strike the butt of the wooden shaft violently against a flat granite boulder. The wood vibrates, the rock rings, but the flint blade remains completely motionless, locked inside a synthetic chemical vise that will hold fast for thousands of years. Archaeological proof of this master craftsmanship was uncovered at the world-famous site of Königsaue in eastern Germany. Archaeologists, excavating the ancient lake margin, uncovered 2 distinct lumps of birch bark pitch dated to 80,000 years ago. Preserved on the surface of one of these ancient pitch pieces was a clear, unmistakable impression, the fossilized thumbprint of a Neanderthal artisan who pressed their hand into the warm, fresh glue 80,000 years ago. Microscopic analysis of the Königsaue pitch confirmed that it contained precise proportions of inorganic soot and organic plant oils, proving that Neanderthals were intentionally altering their glue recipes to suit specific technological tasks. This brings us to a profound, counterintuitive scientific twist that completely flips our understanding of human technological history. In modern history textbooks, we are often taught that the invention of synthetic materials, chemical processing, and complex pyrotechnology began with the birth of ancient civilizations, metal smelting, and early pottery kilns 6,000 years ago. We assume that sapiens were the sole inventors of advanced manufacturing techniques, but the physical evidence from the Ice Age proves the exact opposite. Neanderthals invented the world's first synthetic material, birch bark pitch, over 100,000 years before modern humans ever entered Europe. When your sapiens ancestors eventually migrated out of Africa and arrived on the European continent 45,000 years ago, they did not find a barren wilderness inhabited by simple, primitive brutes. They encountered a deeply adapted, technologically sophisticated species that had already mastered the chemical secrets of the northern forests. Recent excavations in Western Europe show that early sapiens quickly adopted birch pitch hafting technology, learning the exact same distillation methods that Neanderthals had perfected for 200 centuries. The super glue that bonded the weapons of early modern humans was a technological inheritance passed down from their heavy-boned Neanderthal cousins. When you mirror this ancient evolutionary story onto your modern, everyday life, the connections are both humbling and deeply revealing. Today, we live in a world surrounded by synthetic polymers, superglues, epoxy resins, and carbon fiber composites. We fix our shoes with rubber cement, bond our furniture with industrial adhesives, and send rockets into space held together by high-tech chemical sealants. We look at a tiny plastic tube of superglue sitting in a kitchen drawer as a cheap, disposable product of modern mass production. We assume that high-level chemistry requires clean lab coats, digital control panels, and university degrees. But when you look through the objective lens of archaeology and materials science, you realize that your modern tube of glue is the direct descendant of a fire-lit clay pit dug into the freezing mud of Ice Age Europe. You realize that long before human beings built their first cities, wrote their first words, or planted their first crops, our broad-shouldered Neanderthal ancestors were sitting beside hearth fires in dark limestone caves, carefully controlling oxygen-deprived chemical reactions, mixing mineral fillers into boiling tar, and inventing the very foundation of synthetic manufacturing. You step back into your warm, sunlit kitchen on a quiet Sunday afternoon, setting your repaired ceramic coffee mug onto the wooden table. You lift the mug by its handle, feeling the solid, seamless bond holding the heavy porcelain together. You look down at your own thumb, thinking about that 80,000-year-old Neanderthal thumbprint preserved forever in the fossilized birch pitch at Königsau. You take a warm sip of coffee and smile softly to yourself. You realize that your ability to repair a broken object, to bond two materials together, and to use synthetic chemistry to overcome physical limitations is not a modern luxury. It is the living, unbroken continuation of an ancient chemical superpower. A superpower born 200,000 years ago in the subterranean hearths of prehistory. Engineered by master craftsmen who turned the dry bark of a birch tree into the world's very first industrial superglue.